Hi, in this video we're going to talk about plane wave reflection at a planar boundary for normal incidence, meaning that the plane wave is propagating straight at the boundary between two media and the boundary itself is planar. Alright, I've drawn a picture here of what the problem statement is. So we've got medium 1, which has epsilon 1 and mu 1. We've got medium 2, which has epsilon 2 and mu 2. There's an incident plane wave, which is E sub I, H sub I, propagating in direction given by K sub I. There is a transmitted plane wave, which we don't know about yet, and a reflected plane wave, which we also don't know about yet. And I've defined a coordinate system here where Z is to the right, X is up, Y is out of the page, and the z equals 0 plane is at the interface between the two media. So looking back at this incident field, E sub I is pointing in the x direction and H sub I is pointing in the y direction, so K sub I points to positive z. Given that, we can write the expression for E sub I and H sub I this way. E sub I is x-directed, it has an amplitude E naught, and the propagation phase constant e to the minus jkz. H sub I is y-directed. It has amplitude E naught divided by eta 1 because it's in medium 1. And it also propagates and accumulates phase with e to the minus jkz. Now, what about those other fields, though? What are the reflected field and the transmitted field going to be like? And here's the reason that plane wave reflections happen, and it's basically this relationship between E and H. Remember, magnitude E over magnitude H is equal to eta. In medium 1, we have eta 1. In medium 2, we have eta 2. Those things are not equal to each other. So in order to satisfy that relationship between the electric and magnetic fields in a plane wave, and to satisfy the boundary conditions at the interface, we end up with a reflected plane wave also. So we're going to have to find those reflected and transmitted plane waves to find out what's going on. What exactly are the boundary conditions at this interface? The boundary conditions are tangential electric field is continuous, which is written mathematically as surface normal vector across E2 minus E1 equals 0. And tangential H field difference is equal to the surface current, but no surface current unless you're really given some. So then n hat cross H2 minus H1 is equal to that surface current density. But again, unless you're given a surface current density, there isn't going to be one. So then we'll just have that be equal to 0. Now, E2 is just equal to E sub t, the transmitted electric field, and likewise H2 is equal to H sub t. H1, sorry, I'm going to write E1 first. E1, though, is equal to the incident field plus the reflected field. And likewise, H1 is equal to incident magnetic field plus reflected magnetic field. Don't get confused about this. These two are vectors, but they actually point in opposite directions, so a minus sign is going to show up later for those magnetic fields, so pay attention to it. Now, we said that incident field is propagating towards positive z. And the transmitted field then obviously also has to be going in the plus z direction. And the reflected field, it makes sense that it would go to the minus z direction. But do these transmitted and reflected fields have any x or y dependence? I'm going to say no, and here's why. 1, those boundary conditions have to be true everywhere for all values of x and y. That upside down A means for all in math notation. And 2, E sub I has no x or y variation. So it's actually not going to be possible for us to make a solution where E sub r and E sub t vary with x and y, but E sub I doesn't. And third, what makes it even more hard is k1 does not equal to k2, so the two propagation constants in the two media are not equal, and that makes it even harder. But really the key thing is number 1 and number 2, the boundary conditions are true everywhere. The incident field has no x and y variation, so, well, the boundary conditions are true everywhere in x and y, and they're true in the z equals 0 plane. And E sub I has no x and y variation, so in order to make those equations work out, we can't have x and y variation in E sub r or E sub t either. Meaning that E sub r is going to be also x-directed, and it's going to have some amplitude that we're going to give by E naught. That's the amplitude of the incident wave, times gamma, which is a constant that we're going to call the reflection coefficient. Times e to the plus j k1z, because it's going in the minus z direction. Similarly, h sub r is going to be minus a hat y, because minus z direction, so we got to flip the sign of the h field. E naught divided by a to 1 times gamma, so that gives us the amplitude e to the plus j k1z. Then the transmitted electric field is equal to a hat x, E naught times tau. That's another constant that we're going to call the transmission coefficient. That just gives us the relationship between the amplitude of the incident and the transmitted field. E to the minus j k2z. That's a little 2, not a z. They look a lot the same. Whoops. And lastly, ht is going to be equal to a hat y. Notice the plus sign on the a hat y now because we're back to going in the plus z direction. E naught tau over a to 2 e to the minus j k2z. So those are all our field components that we have to relate. Have I written down those boundary conditions already? Yes, I have. All right, so now what we're going to do is we're going to sub in those expressions for the field components into the boundary conditions that we already have. Now the electric field only has one component. It is the x component, and it is all tangential. So that makes our tangential electric field equation pretty easy. I'm going to drop that cross product because it's not going to change our math at all. In which case we have E naught times tau minus E naught times 1 plus gamma is equal to 0. So tau is equal to 1 plus gamma. Nice. Now for the magnetic field boundary condition, again we only have one component for the magnetic field. They're all y-directed. So when I write that out, H2 has the amplitude E naught tau over eta 2. And then we're going to subtract h1 from that, so it's going to be minus E naught over eta 1 times 1 minus gamma, because the H fields have opposite signs, and that's also equal to 0, again because we have no surface current density there. So this first term was H2 and this second term was H1. Now I need to manipulate that second equation a little bit, the E naught, so I can divide through by E naught and cancel that out, and then I'm going to multiply through by eta 2 times eta 1 in order to give myself eta 1 tau is equal to eta 2 times 1 minus gamma. Then I'm going to substitute in my value for tau that I got up here from the electric field boundary condition. So that tau is equal to 1 plus gamma. And then if I put that in and multiply through by the etas, then I have eta 1 plus eta 1 gamma equals, that should be an eta 2, not an eta naught, eta 2 times 1, eta 2 minus eta 2 gamma. Forgot what I was doing there for a second. And then collecting my terms so that I have all the gammas on the same side, I have gamma times eta 1 plus eta 2 is equal to eta 2 minus eta 1. Last thing, gamma is equal to eta 2 minus eta 1 over eta 2 plus eta 1. And since tau is equal to 1 plus gamma, that's going to be equal to 2 eta 2 over eta 2 plus eta 1. Now let's talk about the implications of this for a second. So we've got these two constants that relate the amplitude of the reflected field to the incident field, the electric field amplitudes, and the amplitude of the transmitted field to the incident field amplitude. The reflection coefficient, gamma, has a special property, and that is that since the real part of eta is greater than 0, or greater than or equal to 0, we end up with the magnitude of gamma always being less than or equal to 1. And you can verify that yourself if you have a lot of time on your hands. It actually doesn't take very much time. Tau, on the other hand, can magnitude tau can be greater than 1. And that doesn't mean that we have more power leaving the interface than we have going in. Because remember, tau refers to amplitude, and so does gamma. Gamma also refers to amplitude. The power situation looks like this. The power in medium 1, I'm going to write this as the time average pointing vector. So S1 is going to be 1/2 the real part of E1 cross H1. And remember, that includes both the incident and reflected fields there. And what you get is that is E naught squared over 2 eta 1 times 1 minus magnitude gamma squared. And it's going to be z directed. If we want to talk about the time average pointing vector in medium 2, we got 1/2 real part of E2 cross H2, but those two are just the transmitted field, so then we get E naught squared magnitude tau squared over 2 eta 2 a hat z. And I'm not going to do it here because I'm going to make you do it in class later. But what you find is that these two powers are equal, so we're obeying conservation of power as long as the two etas are purely real and we don't have lossy media. We still obey conservation of power. If we do have lossy media, it's just that then we have to account for the loss in the situation. Anyway, to solve this kind of problem, though, we only need eta 1 and eta 2. And let's do an example to show how this kind of thing works. We have medium 1 is air. Medium 2, let's say it's water. Water has a temperature-dependent dielectric constant, but let's choose the temperature so that the relative permittivity is equal to 81. So that's reasonably cold water, but not super cold. Not frozen, obviously. Both of these things are non-magnetic, so eta 1 is just equal to eta naught, approximately. It's air, so it's not exactly vacuum, but it's close enough. Eta 2, on the other hand, is going to be equal to square root mu naught over epsilon naught epsilon r, which gives us eta naught over 9, because the square root of 81 is 9. Then our reflection coefficient is equal to eta 2 minus eta 1 over eta 2 plus eta 1, which if I divide through by eta naught to make my life easy, it's 1/9 minus 1 over 1/9 plus 1. So that's 8/9 divided by 10/9. So that's actually minus 8/9. So that's minus 8 over 10, which is equal to minus 4/5. So the electric field amplitude is flipped in sign. We get a phase flip there. And the reflected amplitude is 4/5 of the incident amplitude. The transmission coefficient, tau, is equal to 1 plus gamma, which will give us 1/5. And if we look at the power in that situation, then we have the power, the Poynting vector in medium 1 is E naught squared over 2 eta naught times 1 minus magnitude gamma squared, which in this case, 1 minus magnitude gamma squared is going to give us 9/25. And then S2, the Poynting vector in medium 2, and again, that's in the z direction, is going to give us E naught squared over 2 eta 2 times magnitude tau squared, which is, remember, eta 2 is eta naught over 9, so that's 9 E naught squared over 2 eta naught times 1/25. So put the 9 over there, you got 9/25 again, and the two powers are equal, as they should be. So there we go. We did plane wave reflection from a planar interface at normal incidence.